Hey guys, yeah, we're gonna be having a look at electronic control modules. So we're going to start with a humble relay, and we're going to sort of work our way through all the other bits and pieces on the car, as in the engine management systems and the fuel injection. So just a quick brief look around things. This is on this particular model, that's our engine computer, that fella there. That's our airflow meter. The airflow meter measures the amount of air coming through and sends a signal to the ECU, tells it how much fuel to use to compensate. Alright, under here we have our diagnostic plug, which is, I don't know if you guys can see that, that little file there. Okay, that's where we hook our scan tool and get our fault codes that interfaces directly with the engine computer and the various other control modules on the car. Right, and here's our ignition system. Those are our coils, 1, 2, 3, 4. Spark plugs are underneath them, of course. And over here we have our fuse box. So if we lift the lid on that, we can see where our relays live. Alright, we've got a bunch of fuses in here. Those square black things are our relays, which we're going to be talking about shortly. Have a look underneath the lid here. We've got a little map of what is what. So it's got a picture of what each relay and each fuse does. If you look at the map, that corresponds is our row of fuses. There is our row of fuses. It's got an arrow that tells us that's the front. So that's basically the map of what's in here. So if we pull this one out here, this is tells us that's our main engine relay. This one, that one there at the front, that's our horn relay. So they just pull out like that, and that's basically what a relay looks like. We're going to take it inside and have a look at it and have a little talk about things shortly. Alright guys, the 12-volt relay. Here she is, just taken out of the car at the front. This is the wiring diagram of how they actually work. So relays are all numbered so we know which terminal does what. So 30 is always our 12 volts in, so we've got a 12 volt power supply coming in this one on number 30. Alright. 85 is always the earth, so that's going to go to earth. 86 will come from whatever you're going to switch it to. So if it was the starter motor, that would be your ignition switch. In this case, we're going to wire up some spotlights, so this is going to be a spotlight switch. So it'll be a switch on your dash. It'll have 12 volts coming through here. Close the switch, 12 volts is going to come to here. What's going to happen then is it's going to come up and we've got a coil here. Now we all know what happens when we run a current through a conductor. We create magnetism. And that's exactly what we're doing here, is we're creating a magnetic field and we're pulling that switch shut. So as soon as we fire that up, we get a current through there, it goes back down to earth. It's its own little circuit. We get a magnet we've just made here, and that pulls that switch shut. So now what happens is that 12 volts, our extra 12 volts, will come straight up here, straight along here, and it's going to feed these two terminals here, 87. This one's only got one, but most relays will have two up the top, right? And they'll both light up at the same time, so you can use them both to feed things. Or you can just use one, whatever you want to do, but in this case, this scenario, we're going to use two. So we've got two spotlights we're going to wire up out here on our car, big high-powered spotlights. They really suck some current because they're high wattage ones. So we're going to go straight to that, or that to there, and we're going to just earth those to the body of the car. So they've got their own little circuit, and that earth obviously goes back to the battery, as we've spoken about earlier on many times. So that's how they work. So the reason we do that is we've got low current here, our switch is good. There's no current, there's a really low current in that wiring going all the way to our relay. And then we've got a high current coming out here going to our lights, so we've got nice bright lights. Nice bright lights and a nice safe circuit. It's not overloaded and the switch is going to last. And that's why we use the relay. Okay. If you're looking at a relay from the bottom, that's what it's going to look like. This is how you're going to wire it up. This is where you need to know where everything is. So your bottom terminal, that one there, is always going to be a 30 terminal. It should have a little 30 written there. And that's where you put a 12 volt supply straight in there, right? That's 12 volts straight from the battery. That's not through a switch or anything, straight from the battery, pure power source. Over here you've got your 85, that's an earth. Okay, so you put a wire on there, earth it. Over here is your 86. So this comes from whatever you're going to switch it to. So for this scenario we're going to use, again, we'll just use a set of spotlights. So you're going to have a switch on your dash to turn your spotlights on and off. So you wire that up to a 12 volt source under your bonnet, under your dash rather. To your switch, shut the switch, 12 volts coming in there. Goes through that little coil that we talked about. The magnetism is going to pull those contacts together. Now that 12 volts, that power source there, is going to come straight through and go to these terminals. These terminals are going to go down and feed our spotlights. And they are individually earthed. So there's our working relay. Contacts shut, power to here, nice bright lights. Low current on the circuit. That's how we wire it. There's two types of relay. One is normally open, which is what this is. So the contacts inside of there are open till our little electromagnet sucks them shut. Right, so we use that to switch something on. The other type of relay is normally closed. Normally closed, the contacts will be shut and you'd use the electromagnet to actually pull them open. Just want to talk about engine management, talking about control units. We'll start with the engine control module, or the engine computer, whatever you want to call it. All sorts of acronyms and names for it. There's a lot of people call it ECU, which is electronic control unit. Some people call it a ECM, which is an electronic control module, or a PCM, power control module, PCU, you name it, it goes on and on. Basically we're talking about an engine computer. Right, best way to think about it is in four parts. So you've got your input, output, memory, and your processor. Right. So the way it works is you get signals from your various sensors around your engine, and they'll come into your inputs. It'll then go through the processing unit, and that'll compare it with what it knows, what it's been programmed for, and the parameters that's been set for it. It will then make a decision and send signals through the output to operate things. So for instance, if you've got a crank angle sensor, you start cranking your engine, you've lighted up your system because your key's on, your starter motor's cranking the engine over. It's getting a signal here telling the input that the engine is turning over, because that crank angle sensor is telling it's turning over. That's going to go in here, they're going to have a look at it, they're going to say, yep, okay, we're turning over. What we need to do now is we need to send a signal out, we need to fire up our fuel pump. We need to fire up our injectors, we need to fire up our spark plugs, and we need to start this car. Right, and it's all got to be done at the right time, so that's this guy's job. Now as a control unit, most cars have many control units nowadays, so you're going to have at least another one. If you've got an automatic transmission, you're going to have one for your transmission. You'll have another one called your body control module. That controls all your airbags, bits and pieces like that. You'll also have another one for your ABS, anti-skid brakes, traction control. A lot of European cars have anything up to a dozen to even up to 20 modules. This is a basic system on a basic car. All these modules talk to each other, two-way wires, so they're all talking to each other, all communicating on a system that we call CAN bus. Right? It's a CAN bus system. It's two ways. Everything's communicating to everything else. Transmission computer wants to know what's going on in the engine, so it knows when to change gear. We need to know when the anti-lock brakes need to work. We need to know when the airbags need to work. Everything's communicating. Right, that's basically how it works. It's a really simple version of how things work, and next I want to move into just a little bit about fuel injection and the different types. We're just going to talk a little bit about fuel injection. Fuel injection replaced the humble carburetor, and the first system that came along was our what they called single point injection. Now what they did was they used, instead of a carburetor, they used a throttle body bolted to your manifold, which then went to your engine, and they just put one or sometimes two injectors straight into here, and that's all it was, just two injectors straight into a similar manifold than what we had before. This system's pretty much obsolete nowadays, and you're probably not going to come across one. Some of the old Nissans had it, some of the early Falcons, still some American cars use it, but nothing on the domestic market really is single point anymore. It's pretty much done and dusted. It served its purpose. Nowadays, most of what you're going to see is multi-point. Multi-point injection. So if you look at your engine from the top, there's your rocker cover. You've got your exhaust comes out this side. You've got your inlet manifold there. Now you're going to have 4 injectors coming into your inlet manifold on a fuel rail. Usually you'll have an inlet coming in, you'll have a pressure sensor here, and then a return back to the tank. So it'll be coming in that way and going out that way. So what you don't use gets returned back to the tank. It's a pretty good system, it's pretty reliable and pretty simple to use. The reason we use fuel injection is for a thing that your engine management is always striving for, and it's called stoichiometric. Stoichiometric is also known as lambda, or lambda 1 sometimes. What it is a ratio. It's 14.7 to 1. Okay, so every 1 part of fuel we've got 14.7 parts of air, and that's your perfect storm for making a perfect mix in your engine with the least amount of emissions to the most amount of power. That's what we're always striving for, is 14.7 to 1, right? Stoichiometric. And the other type of fuel injection that we come across nowadays is direct injection. So direct injection is very similar to diesels. It just injects the fuel straight into the combustion chamber. So if you're looking at your cylinder with your piston in here, okay, there's your con rod, there's your rings, here's your combustion chamber up here, you've got your inlet valve, you've got your exhaust valve. What we're doing here is we're putting an injector straight in here. The last one we looked at, the multi-point, is would have been on a manifold. Now injector's going in here and getting sucked in, right? Same with our single point, again, is out here and getting sucked in. Our direct injection comes straight in here. Okay, very similar to, like I say, we'll have a spark plug here right beside it. Very similar to our diesel, except obviously on a diesel you don't run a spark plug. Now, the beauty of a direct injection is that you can run it really lean. Okay, they run super lean, which means you use less fuel, there's less unburned fuel, and there's less emissions coming out the back end. So they can come right down to 65 to 1. Right, it's a big difference, isn't it? 65 to 1. That's how lean they can actually get. So with these fellas though, you need to run them on super high octane petrol. They're mainly designed for 100 octane. So if you've got a direct injection car like a GDI, Mitsubishi or something like that, DDI is another word, direct injection. You need to be running it on high octane fuel, 98 octane, something like that. Because otherwise they'll carbon up and they'll become really, really inefficient, and then they'll carbon up and you'll have black smoke and they won't work properly. Great system when they work, not so flash when they don't. Alright, so now we've got a fuel injection system. How do we get more fuel when we need it? That's the big question, isn't it? We want to do more revs, we want to go faster, we need more fuel. So how does that happen? Two ways we can do it. What we're really looking for here is, this is your inlet manifold. Manifold pressure is directly responsible for how much fuel we get in. When we're idling, we've got low manifold pressure, okay, and we've got a high vacuum. High vacuum, so that's the suction, right? So some vehicles will use a thing called a map sensor, and they'll just plug that straight in with a vacuum hose straight into your manifold, and that senses the manifold vacuum. It's got a little diaphragm in here, and it's got a little resistor. And as that diaphragm moves up or down, depending what's going on, it'll send a signal back to the ECU, into the inputs. What happens is when you put your foot down the accelerator, you need more fuel. That low pressure turns into a high pressure, and that high vacuum will turn into a low vacuum, right? So at idle, it's going to be sucking that diaphragm down. That resistor is going to be all the way down here. When you put our foot down, all of a sudden that's going to go up, and it's going to change the voltage that's coming out here. That voltage is going to tell the ECU, hey, we need some more fuel. So then that will come back as an output to our injector, and it'll just lengthen the amount of time that the injector is open for per cycle, and that'll put more fuel in as we need it. So it's a gradual thing. That's a MAP sensor, or manifold absolute pressure. MAP stands for manifold absolute pressure. The other way we do it is on your inlet manifold, there's the air coming in here, through your airbox, through your filter. And then here we put a throttle body and what's called an airflow meter. And that senses how much air is coming through here. So when we open the throttle, obviously more air is going to come through. That is going to send a signal back up to our inputs. So there's more air coming through, we need more fuel, and that'll open the injectors for a bit longer. The airflow meter, or the air mass meter as it's sometimes called, it's the same thing, does the same job. It's probably the most common thing you're going to come across on cars nowadays. There's not too many running the map sensors anymore. Again, that was a lot of American cars, Falcons, things like that. You'd find the map sensors on diesels a lot more nowadays. Some cars will run an airflow meter and a map sensor, and they'll take the data from both of them. And that's how you supply a bit more fuel, by just opening those injectors just a little bit longer per cycle. So every time it comes around, the milliseconds get more and more, so you get more fuel. And pressure is the other thing too. Pressure is constantly monitored from your pump. So your pump is monitoring what's going on in the manifold. The fuel pump pressure will be constantly higher than your manifold pressure, right? So it's just got to be constantly stay higher than your manifold pressure. Your manifold pressure is going up and down, your pump pressure will go up and down with it, right? So when you're at low pressure, you'll have low pressure from your pump, but it'll be slightly higher, but it'll still be low. So as you put your foot down on the gas, you create high pressure in here, and again that creates high pressure in your pump. So again, it's ready to deliver that extra fuel that we need when the signals come through from here or here. The pump's ready, delivery's ready, and it goes. Right, so here we go, guys. Maybe it's time to press pause and go and grab yourself a Bluetooth or something, eh? So going on. Personally, I'm choking on chalk dust, so I think I'm going to head outside for a little bit of fresh air. Right, so out here we've got a selection of Mazda 3s. We've got that one and that one. This is the early model one, and it is 2008 Mazda 3. And this is an example of what we're talking about with the fuel injection here. This is a multi-point fuel injection, so these are your injectors down here, 1, 2, 3, 4. This is our fuel rail, and this is where the fuel line's coming into our rail, alright, and it's going into the manifold and then into the engine. Okay, so that's a multi-point fuel injection system. This one does not have a return line. This is a returnless one. Not uncommon to find that. Right, multi-point injection. Here's our electronic throttle body. We'll be talking about that as well. And the other thing we're going to be talking about is our oxygen sensor. Alright, this is our first oxygen sensor, this one here. It's a wideband. We're going to be talking about that later on as well. Alright, so this fella over here, this is a later model version of the same car. Alright, this one's a 2015. So this one runs a direct injection system. So as you can see, you cannot see your fuel injectors. The reason for that is that they're right under here and they go straight into the combustion chamber. Alright, they're not going into this manifold, they're going straight into the combustion chamber. Right, so you've got a pressure valve on there, sensor valve, and you've got a high pressure fuel pump, which is this fella here. Alright, so you've got a pump in your tank, supplies this high pressure one, and this bumps the pressure up and directly injects the fuel straight into the engine. So again, fly-by-wire throttle, electronic throttle valve. There's our airflow meter on this guy. Computer is mounted under the bonnet on this one. That's your engine computer right there. And again, oxygen sensor down here. All right, we'll be talking about him later on. So those that's two examples of the fuel injection systems that we were talking about earlier on. Alright guys, just going to talk about idle systems. We've got this flash fuel injected engine now. We need to figure out how to make it idle nicely for us. Obviously when the engine's cold we need that idle to be up. When certain loads are on, like your air conditioning and your power steering, again we need the idle to come up. So we need to be able to control how fast our engine idles. So we've got air coming in here, going to the engine, to the manifold. Here's our throttle plate, okay, that's our little butterfly. Put your foot down the throttle, you open that up, air comes through, makes the engine rev more. If you're in gear, you're going to go faster. If you're not, you're just going to rev up, but it's going to make the engine run faster. The more air comes through, the more fuel comes through. So the way we do this is to actually bypass this throttle. So we've got an air chamber here, and what we want to do is get it through to this chamber here and down past on the other side of the throttle. So what we do is drill that out and put a valve through here, put the valve there, put a spring on the end, so the spring holds that valve tight on there. Got our computer up here. So this is just a solenoid like on your starter motor. Just the same thing, just an electromagnet. So we run power and earth down to it, magnetise it. But with our starter solenoid, we pull the rod in. This one we wide it the other way, so we're pushing the rod out. So when we power this thing up, that valve there will come off its seat and be sitting out here. And then the air can come up and go through that little hole and down through here and bypass our butterfly. The more air that comes through, the faster the engine's going to run. Right. So this runs on what we call a duty cycle. All right, we don't just have a straight 12-volt feed there. We pulse it because we've got to be able to control it. So what we do is we pulse the voltage in. So you'll have 12 volts on, then you'll turn it off. 12 volts on, turn it off. 12 volts on, turn it off. 12 volts on. So that's the sort of pattern you get with a duty cycle. We always talk about a duty cycle in terms of percentage, what percentage it is, what percentage it's open, what percentage it's closed, which makes sense. Alright, so we're pulsing that in there. The reason we're pulsing it in is we're getting inputs to our engine computer from things like your coolant temp sensor, which is a thermistor. It's a resistor, a variable resistor that alters the voltage as it gets warm. So that's going to tell us, we start the car when it's cold, we get a signal from this fella here, it says hey, we're cold, we need to bring our idle up. Computer will process it and it will pulse this accordingly. So it'll open that right up so we get lots of air through, so it's going to idle quite fast. As it warms up, the signal's going to, the voltage is going to come down, it's going to tell that to bring that valve back in a little bit, and it'll just slowly close it, and as we warm up that valve will be back there shut, and it'll just be getting a little bit of idle coming around past our butterfly. So the idle speed will slowly come down as the car warms up. The other inputs we get is, like I mentioned earlier, the aircon. Turn the air conditioning on, it puts more load on the engine, so again we're going to need more idle, so that will come down there and it'll come out as an output to open that up a little bit more, and we'll get a little bit of bypass of air coming around there, and the air conditioning's on, idle's going to come up and it's going to be smooth and you won't stall. Power steers, the other one. When you're using your power steering, got it on full lock, you're going into a car park, again more strain on the engine, it's going to bring the idle down, so we need to compensate by using this, we need to compensate to keep it steady. Alright, so we're bypassing that butterfly there is how we do it. Okay, using a duty cycle. Alright, the duty cycle can work either way when you're pulsing it. When you want to open this valve right up, you want the power on for longer periods than you got it off. And you just do it the opposite way around when you want it to shut down, so you'll have the opposite effect. It'll be on, it'll be off for long periods, on for short periods, like that. That's the pattern you get when you put a scope on it. If you put a scope on here, 2 probes with your oscilloscope, that's the pattern you'll get. Right, so that's basically how most throttle valves work, the common one anyway. There are other types which we'll talk about in a minute. Right, so one of the other common forms of controlling our idle was a thing we used to call a stepper motor. These were common on Mitsubishis in the 80s and 90s, early 2000s. Basically just a little electric motor powered by your PCM, and it just wound a valve in and out and blocked off the air hole, or opened the air hole up and let that air bypass through. So that would go, that looks a bit rude, doesn't it? That would go in or out, so if you wanted more air, that would go in. If you want less air, that would come out and block the valve off. So that was how a stepper motor worked. You don't come across them very often nowadays. They're pretty much obsolete, because nowadays we've gone to a thing called the elec throttle valve. Okay, that's what most cars have nowadays, and this is your fly-by-wire system. So we've done away with the cable. There's no cable going to your butterfly anymore. It's purely electronic, and there's no physical connection between your accelerator pedal on the floor and your throttle on your engine. So the system is, you're coming from your PCM, from your PCM you come from your pedal sensor, okay, your pedal sensor is the input. It'll get processed in there and it'll come out to your throttle body, come out to this guy here and tell it what to do. So you put your pedal down here, it goes through there, it says hey, the pedal's going down, and it'll send a signal out and actually open the butterfly physically. It'll have a little electric motor on the butterfly, and purely controlled from here. The advantages of this system are that this guy here's probably better driver than you are, most of us are. So it's going to he'll smooth things out. It takes that erratic driving away where you might be on and off the throttle if you're not that good at driving, going over bumps, things like that, which smooths out your fuel economy. You're going to be look like you're driving better. It also takes a lot of wear and tear off your valve train because you're not on and off the gas and wearing out your drive shafts and bits and pieces. So this is the way of the future, and this is the way we're going now. Electronic throttle valve, and that's how it works. Pretty simple, really.